Teddy and David. They'll be talking about securing embedded projects. So please give them a warm round of applause.
All right, thanks very much for coming out. I'm Dave Anthony, and this is Ted. You're in the Build It track. Hopefully you came here to see our talk. We hope we can give you some good information, stuff that you may be able to take back and use. So our talk is Do It Yourself, Secure Embedded Projects Using Trust.
So why are we here right now? We had a little bit of a fascination with embedded systems and devices over the last year, and we kind of noticed that there's a popularity for secure boot, UEFI, and trusted computing. If you go and look at DEF CON for the last couple of years, you'll find these talks scattered around. So we kind of wanted to merge the two, and we noticed that there was a lack of TPM, which is a component of trusted computing, availability. So I'll challenge you guys to go out and try to buy a TPM that isn't for your specific system. So go out and buy a generic TPM for an embedded device. There's only one I could find that I could purchase without having to sign an NDA with a company, and that was an Atmel TPM. But then I noticed that there are no Linux drivers for that Atmel TPM in TPM-DD, which is the device driver library for Linux. There's code out there for the other devices, but also in order to get that, you need to sign an NDA too. I did not sign an NDA, so all the stuff that we're going to release, right, go ahead and use it. And I'm not going to get in trouble, so don't feel bad for me, as if you would feel bad for me. So finally, we hope to kind of inspire the community. We're not here to market ourselves. You notice we don't have any name associated here other than our pseudonyms, which happen to be our real names. So we're going to inspire you guys, hopefully. So how's this talk going to be structured? We're going to start with a little bit of introduction to trusted computing. We're going to go over that a little quick. It's going to be a little rough. Bear with us. At the end, we want to compare the criticisms to trusted computing, which is a really sore spot for us, especially because we love DRM. Not really. Talk a little bit about UEFI, Linux, U-boot, release drivers for that for the TPM we were able to purchase, and then give you guys a secure boot for U-boot if you're familiar with that. And then finally, some more examples and configuration tutorials and documentations. And then we have we kind of put our money together over the last couple of months, and we were able to buy 100 TPMs and clocks and little breakout boards to give away for you guys today to help bootstart your projects. So what I'm not sure how to give these away yet. Oh, okay. What I'd like to do is give 50 of them away if you can suggest to us afterwards like a cool idea for using trusted computing or TPMs in embedded projects. The additional 50, I'd like to ask for a $5 donation to Hackers for Charity, and then I'll give that to them anonymously, if you guys are okay with that. All right, let's roll.
All right, so part one. Maybe you already came here with a little bit of knowledge about trusted computing. If that's the case, bear with us for a little bit as we get started. We want to bring people who are new to this, give them a little bit of information as well. So basically, a TPM or a trusted platform module is a chip which implements functions and capabilities outlined by the trusted computing group. They have a specification document that it adheres to. And these provide very powerful capabilities, and these capabilities can also be limiting. So for those of you who kind of roll your eyes at trusted computing because it can be used for bad, we will approach that. We're not naive. We are aware of these criticisms. So we'll get into that a little bit later. But one of our goals here is to minimize the pain about learning about TPMs. Trusted computing can be a little bit complicated to get into, and we hope to give you a little initial brief on that. So anyways, let's see. Okay, so the goal of this presentation is to be, number one, provide you with some real-world knowledge of how TPMs work and show you how they can be used in a secure or trusted boot. We're going to explain the differences between that. We're going to show you how you can actually use TPMs in the software world. We can use it for measuring software integrity. That can be local or remote. And hopefully you guys will actually have better ideas than we can even show you. So we'd hope to inspire your imagination with this talk. So let's get in, excuse me. Let's get into the building blocks of what makes up a TPM. It's a physical chip, excuse me. So it contains such building blocks as a cryptographic processor. So we are able to perform certain cryptographic functions, hashing, The TPM includes protected storage, it includes non-removable private keys, as well as measurement registers. And these measurement registers are kind of integral to the discussion of a TPM and the understanding of it. So we have these things called platform configuration registers. Each of them are 160 bits wide. They're just a place for storage. There's 24 minimum outlined in the TPM specifications, and this is not writable. You can't write to these TPMs. The only thing you can do with them is you can either reset them, you can read from them, or you can extend to them. And the extending to them is the interesting part. So basically, let me elaborate a little bit on that. We have basically this extend function. So when you extend to it, you're hashing, it's kind of like a rolling hash, if you will. You can use it on any time you're executing code, you can extend that code to the PCR. So you can imagine as your machine boots up and you're carrying through this process of execution, you can extend to the PCRs, and that kind of tracks the path your machine's taking. So another thing we wanted to point out is we kind of wanted to, we presume you know a little bit about asymmetric key cryptography. We don't expect you to be, real experts, but as long as you're familiar with the general concepts, we think you'll be fine to follow this. Remember, a TPM is just a passive device that provides building blocks for your projects and ideas. In order to use the TPM, software support's required, and adding a TPM to your system without software is also not really going to do anything. So I'm going to go through a couple terminology and vocabulary things here in trusted computing. The first of which is ownership. And I guess I just want to say that some of these concepts are just a little bit new. You'll probably be able to pick them up, but it's good to go through them for those who don't know. So taking ownership. This is the first step. You would like to take ownership of a TPM so you can do more with it. You're going to be setting basically an owner password once you take ownership of this TPM, and that allows you to create what are called a storage root key, which is going to be a root of trust of creating other keys. We'll get into that. But when ownership is established, you create a new storage root key and a new TPM proof value. So then we have different types of keys, of course. We have the endorsement key, or the TPM identity. This can either be created at manufacturer time, or you can, if you buy a TPM that doesn't have it burned in, you can burn it in yourself. That's a point of, focus. If you're going to be buying a TPM, you may want to consider that, because once you write and burn in that endorsement key, you can't do it again. So that's going to be permanently with that TPM. Then you have the storage root key, which, like I said before, it's created when ownership is taken of the TPM. So new owner, new storage root key, and this is the parent key when further keys are created. And then we have things like attestation identity keys. These are they're never used for any encryption. They're used for signing things, and they're kind of basically like a temporary identity. You can create more on the fly. You can get rid of them. You can use them for basically attesting your identity. So there's also other types of keys. You can signing keys, regular storage keys, etc. But that's the basics. So then there's these three concepts of binding, sealing, and quoting. Binding is just a term that it describes data encryption with the TPM endorsement key. That's all it is. Sealing is a little bit more interesting. That's the encryption of data that is also bound to, so I mentioned those PCRs. They're getting extended. As you measure things, they're changing. You can read from them. So the sealing is encrypting data. Having read from those PCRs, you kind of associate that with the PCR values at the time of encryption. So as such to say that to decrypt any data from that point that was sealed, you'll have to have your PCRs in the same, they will have to have the same values in them. And then you also have quoting. It's like sealing, but it produces a signature. We'll show you ways you can use that as well. So, I want to go over two more concepts, attestation and appraisal. Attestation can just be simply described as the vouching for the accuracy of information. And appraisal is more of like using that attestation, using that report, I guess, if you will, to make a decision, almost like a whitelist. Appraising is, using a way to almost use a whitelist for what your machine's allowed to do. And finally, we have two concepts for measurement. In this talk, we're going to be talking about a static root of trust, which we're going to kind of talk about in the concept of a secure boot or a trusted boot. And we have also a dynamic root of trust, which you can initiate at any time during your machines, while your machine's running. And we'll show you ways in which you'd want to use that as well. So, kind of went through that really quick. Didn't get too much into detail on all those vocabulary terms. Ariel Siegel has this Intro to Trusted Computing 101. That's on opensecuritytraining.info's website. They have 2 days worth of slides and, I'd say at least 30 videos. It's good if you want to get into learn more about trusted computing. So yeah, go to this website and trust us. It's a good shortened link. So, I guess I'm going to just say it right now. We're cognizant of the fact that there's a lot of criticisms in trusted computing, and we are aware of that, and that's why we brought our tinfoil hats. We're going So rather than taking a real Donnie Downer kind of view on these, we kind of want to offer alternative ways to look at it. Yes, trusted computing can be used to enforce DRM. Yes, it can be used for multiple things. The first of which is this remote attestation abuse. There you go, yeah. This is kind of a scary one to me. So just for sake of example, go with me here. We wanted to use a Bank of Antarctica. I hope that doesn't exist, but say there's this hypothetical Bank of Antarctica, and they provide a service, and you guys are all members, and you want to check the status of your bank accounts. So you have your we'll say you have a tablet, and anytime you want to connect to use our service, we want to make sure that your machine's in a state that we like. So when you connect, we remotely attest the state of your machine, and if we don't like that state, we can do things like, okay, well, we can remove service until Ted figures himself out. We can't deal with you. So obviously that's like a pretty bad thing, or it puts a lot of power into someone else's hands. Maybe you can use that in a creative way though. Maybe you can use it for your embedded project. Maybe you want to test the state of your devices to make sure they're working. So could be bad. Hopefully it's used in a good way. There's also what we want to cover is the manufacturer trust. If you guys remember the endorsement key, that's a big thing. It can't be changed. So if you're buying a TPM or a device with a TPM that has that burned in, do you know that your manufacturer didn't copy off your public key? And then if you combine that with the user registration, if you were able to, say, buy a tablet and you registered that tablet and they copied off your public key, well, you almost have like a perfect pairing of a device to a person. So it's not the best. Maybe an alternative would be just to buy an EK-less TPM. It's just a thought. And then we have privacy. I talked about these attestation identity keys. You can change those. You can change them for every service you want to use your TPM with. If you don't change those, you kind of are making a mapping. Everyone, if they were able to coordinate their efforts, they would see, okay, you're using Bank of Antarctica, you're using Service X. Almost like the concept of like a super cookie, right? If you're not changing it out, it's kind of fingerprinting you to people. So as long as we raise awareness about those keys and the fact that they can be changed, you can kind of stop that critique. So, booting securely in the non-embedded world. Boot. Okay, so booting secure in the non-embedded world. We have some examples. For instance, OEM custom checking of signatures on firmware updates. That's an example. UEFI. Any Windows 8 certified device is going to be making use of this, which includes multiple certificate stores. You can interact with TPMs. You can do secure boots. Very cool. And you also have like a modified grub bootloader you can use to work with TPMs. And you have this Intel's TXT, which is their implementation of DRTM, or Dynamic Root of Trust Measurement. That can be implemented during runtime of your machine. We'll get into that in a little bit. So basically, we have this concept of a root of trust. Let me try to visualize it here for you guys. You anchor that at a root of trust, and then you implement measuring at each execution of pre-OS code. So you shrink the attack surface with a longer chain of measurement, and pushing the root of trust to the far left as possible. If you do not measure a component or a portion of executable code, the measurement chain is then broken, and you cannot perform checks or attestations from that point forward. A dynamic root of trust measurement will work, but that's creating a separate measurement chain, as you can kind of see here. So that doesn't make any assurance about system integrity from that point forward. You can use that for things perhaps like starting a VM and trying to measure or test the state of a VM. So it's just creating you can still test or measure things, but it's just creating a separate chain. So just to recap measurement, let's see. So think of it as a fancy word for secure logging. System designers can implement a static or dynamic root of trust measurement, but it's a struggle, right? You may be bound to the implementation of your OEM or system designer. You may not have full control over what you want to do. So measuring all the executable code in your system startup or anything else, it's challenging. And that's no joke. So I'm going to hand it over to Ted now and he's going to talk about TPMs on your embedded device.
Okay, everyone take a breather. We're over. Oh, man, that was hard. Okay, so how do we use these concepts for our embedded devices? That's why we're here. Let's pick our favorite embedded device. It's a BeagleBone. I like BeagleBones a lot because of a few things. At the bottom, I say one micro USB gets you 4 things, and that's a JTAG emulator, USB power, USB Ethernet, and a console. With one USB, right? So one thing attached to your computer gets you all these components, and you're up and ready to develop and debug on this BeagleBone. It's about $87. So it has a couple extra things too, one of which is 96 exposed pins, which have up to 7 configuration options per. There's a lot of things that you can do there. A lot of creativity you can apply. And your favorite Linux distribution probably runs on this BeagleBone. If not, it's somewhat trivial to get it to run. So what does it have in it? Here are some of the basic components. 5, 3.3, 1.8 volts over that expansion board. It has Ethernet. We see a memory controller at the bottom, USB. It has a TI AM3359 processor with 256 megs of RAM. You can buy other system on boards that have more than that, but this is okay for what we're going to do right now. 87 bucks. Has a lot of other things too. Just throw a bunch of little blocks up there to kind of cover that. Of which I'm going to highlight in blue the things that we're going to utilize and green the things that we need to pay attention to. And I'm also going to put timer up there in red because we need a timer for our TPM. Unfortunately, if we use the timer on the board, we're going to run into some problems. So I'll say for testing only, we can use that timer too. And then finally, our TPM is going to sit on the I2C bus and talk over I2C to the BeagleBone. So for that TPM, we're going to use 4 pins other than the power and the ground, 2 for our I2C bus. And so we're going to talk to the BeagleBone, to the TPM. We're going to use the exposed pin sysreset N, which is bound to the processor's soft reset and hard reset on the board. If you pull that pin in a different direction, that CPU is going to reset. So if you push the reset pin on, or the reset button on the board, it's going to pull that pin in a different direction, and the CPU is going to reset. If you issue reset to the CPU, that pin will also be pulled. So I talked to some of the designers of the BeagleBone, and I asked them if it's ever possible to disable that functionality. They said we can change the clock on that so we can make it pulled for a different time, but we can never prevent that pin from being pulled when we do a soft reset. So we have assurance that when that CPU is reset, that pin is going to change direction. And finally, we're going to use an external clock. We need to use an external clock because we need to assure that our TPM cannot be attacked in software. So imagine this is your attack model. Do everything but hit the hardware, right? I'm going to give you root on it. I'm going to allow you to load your own kernel, anything you want. You just can't touch the hardware. So if that's our attack model, and we're using a timer on the BeagleBone, it's possible for someone to change that MUX configuration for the timer and disable our TPM. Disable it by screwing with our clock. So it'll still work, but it's not going to give you expected data. So here's the schematic for that. I'm glad you can all read that right now. The software for getting this running in U-boot and Linux, the driver for it, is on my GitHub. We'll pass these slides out to Shmoocon afterwards. If not, write this down really quick. Go. And then we also have a UEFI modified security package on GitHub as well. The default security package, and we took that from Tyanocore. The default security package only uses memory mapped I/O to talk to a TPM. Unfortunately, with the I2C bus, we don't have that option. So I kind of mucked around with the security package and tried to make it more flexible. I did a really poor job. The answer is it does support I2C. I'm not sure if it still supports memory mapped I/O TPMs, but who cares? All right. Manufacturers that make TPMs right now in blue are ones that you can purchase that are discrete devices that's not bound to the system that you purchased. So it's not like going to eBay and saying, I have a Lenovo, whatever, here's the TPM that I want. You can absolutely do that, but here you can buy these and start using them for your devices right now. Out of which, I was only able to get an Atmel chip. That's the only one I could actually put money down and get it. The others, they'll advertise it in their product catalogs, but I wasn't able to find a way to purchase them. I started like the live chat where I'm like, hey, I want a TPM now, and they're like, well, sign this NDA. I'm like, no, and then I close it out, like angrily. So like they're like, oh man, I can't believe that guy just closed out my lot. No, that's not how it happens. So it's the 1897 SC3204T if you want the I2C chip. Otherwise, you're getting an LPC chip. About $6.30 to $6.50, depending on where you're buying them, and the configuration of the TPM. You get it from DigiKey, Mouser, or AVNet Express. And then there's also an option on each one of these sites for purchasing an EK-less TPM. That means that EK identity of your TPM isn't on there. You have to do it yourself, which just gives us a little bit of assurance that the manufacturer doesn't know that public key is bound to the person who's making that purchase order, right? So they can't put it to your credit card and say, hey, I know Ted bought this. So I suggest getting an EK-less TPM. All the TPMs I have up here are EK-less, so you have to generate the EK before you start using it. All right, let's focus in on the things that I called out. We need a board. We're going to need an alternate storage. There's also something in green that I kind of glazed over. We're going to need a TPM, and we're going to need an external 33 megahertz clock. So they're going to suggest to you that you get this really nice, solder mount clock. I'm really bad at soldering, so I bought a SOIC package. And that also happens to be A, cheaper than buying the surface mount clock, and B, programmable. So now, I'm giving all those out too. Now you can actually change that clock and test to see how the TPM responds when you give it something other than 33 megahertz. So I thought that was a little fun. I saved a little bit of money, and it's easier to solder. Whoa, it's blue now. All right, so using those things, let's create a static root of trust measurement on the BeagleBone. Okay, I don't want to run through this too fast, but it's going to be a lot of information. We have about 20 minutes left. So before I start, there's a lot of potential for error here. A static root of trust measurement implies a set of routines secured from any software attack possible. So remember that attack model we had. So in order to do that, we have to prevent writing to the thing that's going to initialize our static root of trust measurement. Well, MMC0 on the BeagleBone has a write protect pin. It's exposed at P842 on the BeagleBone. Unfortunately, it's multiplexed with other pins. So if I'm controlling the software, I can change that, and now that storage is not write protected anymore. So we're going to give you a couple of suggestions. Here are our options. So the first option, which is probably the best, is to use a second storage device, MMC1. And then on the BeagleBone, we pull the boot configuration such that that becomes our default boot. Afterwards, if you change those pin settings, it doesn't matter because the BeagleBone is only looking, and the processor is only looking for its boot configuration based on the pull of the pins when it hits a reset. So we're okay there. Similarly, if we're feeling a little bit more fancy, we can also grab that code from a USB or SPI, something that we know is write protected. In the first, we have to pull the write protect pin on that MMC1. Or we have this really badass option, which is we can permanently disable writing to any one of our SD cards and put that into MMC0. We write a program CSD command, command 27, pulling 13 high, and then that chip, that storage card will never be able to be written to again. So it's not very flexible, but it'll work. All right, so let's do a static root of trust measurement. Let's start with this AM3359 processor. Has some ROM code, and it's going to go to its default boot configuration, and it's going to execute that code. So we just said that that first thing that it's going to boot, we have on write protected storage. So that default device now at MMC1 is going to look at partition 1 for a FAT, and it's going to look for a file called MLO. In TI's world, this is Xloader. In U-Boot's world, this is the second phase loader. We'll talk about that. And we assure that this is write protect storage because we're doing some modification out of the options presented before. So second phase loader, the first phase would be the ROM code, the stuff that you can't change that's being executed on the CPU. And this is where we initialize our static root of trust measurement. So code that cannot be changed is going to start up the TPM. And then after that, going forward in our execution, that SPL code, the MLO, is going to measure U-boot or UEFI, and then subsequently measure everything it's about to execute after that. So after MLO, we can start executing from read-write storage, because now we're measuring. So, okay, now we have a static root of trust measurement. Let's use that for a secure boot. So we're going to implement this version of secure boot with sealing and unsealing. All right, little recap. As long as the boot pins are not changed, this device is write protected. So we can execute MLO, and then MLO can read U-boot. After which, we're going to do a PCR extend of the hash of that U-boot that we're about to execute. And then we try to unseal the state of U-boot that we had sealed previously and that we know is good. Depending on the output of that unseal, we can make a decision, a success or failure. On success, we can start executing U-boot. Failure, we just halt the CPU. So this is what we're doing in the TPM, this little green box here. We're extending and we're trying to unseal. Now this looks a little weird because I didn't mention a lot of things that we have to do before we can get to this step. So let's recap what the MLO is doing. It's initializing a TPM, so it's running a startup command for the TPM, it's doing a self-check on the TPM. It's verifying configuration, so like A, you took ownership of it, it has an EK, and you have some protected storage on that TPM that is going to load some sealed data. We're going to read U-boot, we're going to extend a PCR with a value of that hash, then we're going to read a sealed U-boot blob, and then we're going to try to unseal that blob. So, all right, now it's kind of a little bit more obvious. Before we can secure a boot, we have to seal a blob for U-boot. But one more thing. During the secure boot, that second phase loader is verifying the U-boot it just read as the expected U-boot by sealing the extended PCR. So remember, we need to enforce the state by sealing those PCR values. So we cannot unseal unless the PCR values are the same as when we had sealed previously. That means that we must seal while the PCRs are correctly extended. So how does this look in a little block diagram with a lot of my favorite colors? Well, we're going to read U-boot, extend, unseal that blob, and then we're going to run into a problem because we don't have a sealed blob. It's going to mess up. So we allow execution to continue. We're going to execute U-boot, and then once U-boot is executed and extended, we're going to write a blob. And then later when we want to do a secure boot, we're going to recompile that MLO to prevent that oh my god problem, allow it to read, extend, unseal, and then make that decision. So that oh my god problem requires us to recompile MLO. That's not really a good thing. And then afterwards, we have to prevent arbitrary writes to the access of that blob on storage. So in this example, we bind that blob to a physical presence state for the TPM. If that physical presence isn't asserted, then we cannot read or write. So if MLO is enforcing a secure boot, changing the U-boot binary is not possible. That's not very flexible. So I just want to call this out. This is a problem. And another aside, we use the TPM's NVRAM to enforce the protected storage of that blob, but also because it's an agnostic way for us to read and write, so we don't have to support file systems and all that kind of jazz. So, okay, let's do that again, right? Let's do a static root of trust measurement for a secure boot, but this time, instead of sealing and unsealing, let's use signatures. Right, let's see how much flexibility this gives us. Start again, reading the MLO, and then having the MLO read U-boot. So we have our static root of trust measurement initialized. This time we're going to read another thing too, which is going to be a signature for that U-boot. We're going to extend, and instead of unsealing, we're going to replace that with an RSA verify. So we're going to try to verify that signature. If it matches, then we're going to make that decision of whether we want to succeed. If it doesn't match, we're going to fail and halt the CPU. Now, the only thing we're doing for the TPM now is this PCR extend, and even that is optional, right? We can implement signature checkings without a TPM. That's not new. But in this example, we're not only checking the signature of code that we're about to execute, we're logging that measurement of it. So we're going to maintain a measurement chain of everything we're about to execute. And that's going to give us a lot of flexibility in the future, which we'll talk about. So what do we do a priori in a signature-based secure boot? Not very much, and there's no oh my god problem in this case. We compile MLO, we give it a public key, and then we sign uboot. And every time we want to change that, we just sign uboot again, and we replace it. So expected updates to uboot will contain a valid signature, not require any change. Awesome. In the secure boot enforcement. And then the static root of trust measurement using signatures or certificates does not require a TPM. We can do this right now. But it's not really a root of trust measurement if we're not measuring anything, right? We're missing that secure logging block. So I'm going to argue right now and say that we need a combination of both, and I'm going to show you why. We need a seal and unseal, that kind of not robust mechanism, and then we need signatures as well. So, okay, we arrived here. We succeeded in the signature or the unsealing, and we're going to execute uboot. This is what we get. We get a prompt at uboot. Uboot has an interactive component to it. This could be a problem if we interrupt that boot process and we do something like load a binary to a memory address, and then later our kernel executes some code that's dependent on that memory address. Or we set an environment variable that lets us change the functionality of the kernel once it's loaded. So that may or may not be an IP address that's existing on this hotel network that's serving up NFS. I'll let you guys figure that out. So what we really need to do is use signatures, but also extend PCRs every time we run a command inside uboot, or we set an environment variable inside uboot. So, and then we repeat this process for the kernel and then every subsequent piece of code that needs to be run. So uboot, and then uboot's going to take in either just a kernel or a kernel RAM disk, and a flattened device tree, and anything else. So we've implemented this all in uboot right now. And then there are other ways to execute code, right? If you do just kind of jump to a location in memory and start executing, we know that uboot will have measured that, and then it's the responsibility of that code to continue that measurement. If it doesn't, that measurement chain is interrupted. So this is called libsboot. It's only implemented in uboot right now. It's an example of secured boot modeled loosely after Chromium's vboot. Chromium team, if anyone's here, you're epic. I love your code, and I love borrowing from it. I've put this on my GitHub as well. I would not make any verifications to the security of this code, right? I've been the sole person, aside from Dave, who he's not good at coding like me.
Sing.
So I make no verification, right? It hasn't been independently reviewed, and the problem with that is it's hard to get a TPM to run on these devices, so that's why I'm giving these out for you guys, so you guys can go and review that code and tell me how I suck. So good luck.
All right, so I'm going to continue with what Ted's talking about, but maybe you don't really care about embedded devices at all, and you were curious about ways you can use trusted computing in the software world or just in other ways. So I'm going to talk to you a little bit about that. The Linux Integrity Measurement Architecture, this is a very cool thing. So since kernel 2.6.30, this has been added to the Linux kernel. It allows the Linux kernel rather to calculate hashes of files and applications either before loading or memory mapping them or before execution. So it originally allows just the writing to this log file, and what you can see here is that log file. And in order from left to right, you can see the PCR, which default PCR these things are stored or extended to in is PCR10. You can see that the SHA-1 of the file name plus the file contents, the subsystem it is, in this case it's IMA, and then a SHA-1 hash of the contents of the file, and then a hint, file name hint. So as you load things into the kernel or before execution starts, you can actually make a log of this. Now, this isn't a log of the PCRs being extended. This is rather a log of, like I said, the hashes. So you're getting a log of the hashes, but at the same time, unbeknownst to this log file, you're also extending to the PCRs. So that's updating, I guess, under the hood, so to speak. But it's important to note,
So everything that we had measured before that, the Linux IMA is also going to take into account. So when it starts up, it's going to take PCR 0 through 7. It's going to make an aggregate of that value, and then it's going to log that and extend to 10 as well. So all that mumbo jumbo I mentioned before in U-boot and in any other loader that you have, if we did any measuring there, it's going to be made aware to the Linux IMA as well.
Exactly. So you don't see it carried through, but you see what it was before the extensions continue. So we have this log. That's cool. I mean, I don't really like log files. You guys probably don't either. So what can we do with it? Well, you can take the aggregate value that was stored in PCR10 throughout all of these measurements. You can combine it with an AIK or an identity key, and you can add that with the log file, and you can send a quote using OpenPTS. Basically, you can send this quote to a trusted third party to then give you a success or a failure. Okay, so that's a little bit cooler than looking at a log file. But again, remember, for this success failure to happen, there has to be that initial, the a priori recording of what we think are good values. So,
For a standard Linux distribution, it's about 2 megs for all possible execution. So if you're putting that into an MySQL database, about 2 megs of data.
So, to recap, IMA calculates the boot aggregate and records things, subsequent executions or memory mappings. OpenPTS is what allows you to send that quote to a trusted third party. I guess a real-world example of this is this Strong Swan. So, with Strong Swan, you can take that aggregate value, that quote, you can send it to, and I guess an example would be like an enterprise. I went back. Okay. So you can take that quote that we just talked about. You can send that to an enterprise who maybe it's, you're logging in via VPN and they want to attest to the state of your machine before they allow you onto the enterprise LAN. Well, you can do that with Strong Swan. You can either attest the value of that person, and depending on whether or not they fit the policies that you created, they can either segregate you to a limited LAN or allow you full access. So that's kind of a cool example that you may think about using. Or maybe you don't like using trusted third parties and you wear a tinfoil hat. Since kernel 3.7, IMA has given an update. There was a patch to it which created IMA appraisal. So rather than just creating a log file, you can actually prevent the loading of modules if you so choose. So a lot of people may find that a little bit more interesting than just creating a log file. So moving on. Appraisal, to go deep dive further on that. Appraisal, all it's basically doing is creating an extra file attribute called a security.ima. So that's created initially, and then when the same file is about to be memory mapped or executed again, you can compare that to the initial measurement and then make a decision based off that. So signature extension allows you to create that, allows you to sign the hash stored in the security.ima, and directory extension allows you to create an HMAC for all the file's metadata, including the security.ima attribute. But HMACs require a symmetric key. So the reason we need an HMAC, not a signature, is because we may change file metadata during runtime for changing permissions, inode change, etc., things like that. So HMAC exists to protect the data from offline attacks of the file system, things like booting from USB, for instance. So we store the HMAC key using Linux trusted keys, which allows us to seal the key to a known state, similar to that pairing of U-boot to PCRs that we talked about earlier.
So there are 2 ways to put keys inside the Linux kernel, and that just holds keys in memory and that can't be accessed by userland. So there are encryption keys that we could use and then trusted keys. In order to use trusted keys, we need to have a TPM because the trusted key implies some state of the PCR before that key is going to be decrypted by the TPM and then thusly allowed to be used by the kernel. I say allowed, it's not really a decision that it's making. If the PCRs aren't in the right state, it won't be decrypted and it won't be able to be used. So by implementing a trusted key to be used for the HMAC, we know that if we boot it in the correct order, meaning that we didn't boot an alternate method, then that symmetric key is going to be released, and we can use that when we're making metadata changes to the file system, such as moving a file from one directory to another. So we'll kind of finish up here, bringing all this together in a real recap, show you some of the gaps, recover our ideas, and then let's try to figure out how you can help us. Help you? What? Okay, so booting, Secure Boot can be used to maintain expected boot options. The embedded bootstrap does not often change while in production, so this could be used to our advantage. And then with user programmable key stores, we can allow the device owner, right, not the manufacturer, to make that decision of when they want to update their firmware. So instead of Microsoft or any other company that releases signed updates coming to your device and your device willingly accepting them, which is great, now we can put a user in the middle of that and have them make that decision as well. So maybe they might not want to accept one firmware update. They don't want that to be pushed to their device to change the state unbeknownst to them. So measurement is how we will accomplish this, and it can definitely continue past booting for us to make policy changes about the state of the device when it's running an operating system. This is not going to protect you against runtime attacks, so if you have a poorly configured application running and that gets owned, and then from there on out, the device is going to be insecure. But you're going to know if any code gets executed or while that code is being executed to create that exploit or to run that exploit. Afterwards, it's okay for that exploit to lie to the measurement log, but we will have that initial measurement of when that happened. And when we go to make a policy decision, that won't match our pre-computed policies. And then finally, attestation. We can do this remotely and locally, and we can do it in a privacy-preserving manner, which is great. And I think this is one of the sources of contention for criticisms against the TPM. As long as you're doing proper key management, I know that's really difficult when just like, oh yeah, do proper key management, and all your life is going to be easy, right? Sure. But so with distributed key infrastructures, and I'm going to caveat this right now, I can't find a distributed key infrastructure implementation that allows you to use TPMs out there right now. I've searched for like a couple weeks trying to find this stuff, and every once in a while when I get bored, I go and search again. There's not too many terms that I can use, but if someone could create a distributed key infrastructure that allowed me to remotely attest to the state of my TPM, and I could create that infrastructure and stand it up myself, that would be amazing. So, because that would allow user-defined or enterprise and company-defined abilities to do that remote attestation.
So we wanted to also point out a few other things. Maybe you like to use VMs. If there's any Zen fans in here, I think it was Intel and IBM. They paired up to make it work with the Zen hypervisor. So as you can imagine, if you have a hardware TPM, it's kind of a one-to-one mapping to the host OS. So if you have multiple VMs and you're trying to use the same hardware TPM, you can see where that may run into problems, right? You're storing measurements, you're comparing things. If they're all trying to use the same TPM, we run into a trouble. So the way they've implemented it is you can spin up and spin down virtual TPMs to associate with each of your regular VMs. So if you wanted to use maybe an application you develop that makes use of trusted computing, you can do so inside your virtual machines. And there's also a software TPM. This is really cool. IBM made this. You can use it to develop for. The idea with this is that you can, anything you develop, any application that you develop that works with the software TPM should be able to be swapped right in and work right away with a hardware TPM. So this is really cool for a number of reasons. I guess one of the primary ones is you can spin up multiple software TPMs and communicate with them over TCP/IP, and you can do things like test migrating of keys. So I don't think we pointed it out, but you know, you're not going to be stuck with the same laptop for the whole. You're not going to be typically with the same computer throughout your enterprise for the rest of forever, right? So you're going to have to maybe at some point migrate those keys off of your TPM. Well, an easy way to test this would be to do with multiple software TPMs, because whatever you program should be able to be hot swappable with a regular hardware TPM. Should be, but that's up to you.
And then finally, I just want to put a note out there that maybe this is a little overkill. Maybe for your embedded project, security doesn't need a TPM. So I wanted to call out this other chip that Atmel has that you can purchase, is pretty inexpensive, AT-SHA 204, which gives you that protected storage component and allows you to put access control onto that protected storage so that things will be released in, let's say, only when you're attesting or assessing physical presence. And this thing doesn't include crypto functions, so if you need any type of crypto functions, this is not the answer for you. But you could put sensitive data on here like symmetric keys or private keys. So finally, recap. we're a little low on time, so I'll just throw this up there. There's a bunch of links in our notes as well. So when we release this slide presentation, I hope that if you have an interest in this stuff, you'll go through it and look through all of our notes as well. So thank you for being here. In our TPM kits that we're going to try to give away after this, we have one of these Atmel 1897 SC 3204Ts. We have a 28-pin SOP breakout for you to put that on. I apologize, I ordered these in bulk from Bangkok, and they're really hard to solder onto. So you can do it because I can do it, and I suck at soldering. I also have a Maxim DS1077Z, which is a 66 megahertz programmable oscillator. You divide that by 2, and you'll get 33 megahertz for the TPM, and it should work great. And then I have an 8-pin SOIC breakout for that. I wanted to put another note in here, too. These Atmel chips cost about $6. I talked to, also on live chat, to someone from Mauser, and they were able to give them to me for $2 because I said I was going to come here and give them to all of you. So I want to say, give a thumbs up to Mauser for that. Everywhere else, yeah, that's awesome. So everywhere else, the live chat people, although they're fun to talk to, they didn't cut me this deal. I guess my sweetheart talking skills weren't up to par that day. So this is where you're going to get. I have a link on here too. That link will go live as soon as I start handing these out. That just gives you a tutorial about how to put this together. Otherwise, all the code's on GitHub right now. Go ahead and have fun with it.
Thanks for coming out.
So what I want to do is I'm going to take all this stuff that we have and go over to the room. I didn't see what happened. What happened?
Who was that, Heim?
Oh, nice, nice. So I'm going to take these out there. I want to go by Raphael Mudge. I'm going to go right across from him and set up shop.